Good morning. My name is Rami Khoder. I got my PhD from Versailles University in France and Lebanese University in Lebanon. My topic for today is a vertical handover decision using machine learning in vehicle platon, supervised by Professor Rola Naja and Professor Samir Tohme. The outline of my presentation, I will start by an introduction about my topic, followed by the proposed vehicular architecture. Then I will introduce the vertical handover decision-making using machine learning techniques. Then I will focus on the machine classification matrix. And finally, I will make a conclusion and introduce our future perspectives. The vehicular platooning. The vehicular platooning is a technique where highway traffic is organized into groups of close following vehicles called platon. By using vehicular platooning, we can enhance the traffic efficiency, the road capacity, and the safety of vehicles. We can reduce the driver's error and traffic congestion, and we can transmit efficiently information among vehicles platon. The handover is a process of moving an active call or data session from one cellular network to another, or from one technology to another. It consists of three phases. Phase one is the initiation phase, where users, after studying the degradation of link quality, start collecting parameters from neighbors. These parameters will be used in the second phase, which is the network selection decision strategy, where the selection is done based on two different techniques. The first one is the algorithms, the second one is the fuzzy logic, and in the last phase, the handover executions that have one main objective, which is having a smooth handover between existing network and target network. The second outline, then we will start by the proposed vehicular architecture. The first step that is related to the interference caused by disruptive vehicles at night, where we have two different lines. The first line is reserved for vehicle platooning. The second line is reserved for disturbing vehicles that will interfere the connection between vehicle platons. In the second step, we have added the sun, where we will evaluate the visible light communication performance in the presence of two sources of interference, the disruptive vehicles and the sunlight interference. The sunlight interference is studied between 6 a.m. and 18 p.m. This figure shows the variation of the sunlight intensity throughout the day. The intensity of sun increases all the day until noon. From this moment, the intensity of light will decrease as we advance from noon to evening. Now we will start by the vertical handover decision-making using machine learning technique. This platform consists of three sections. Section one, the data file collection, where the data is collected by a series of simulation. We have simulated two steps based on Sumo and Omnet++. 100 platons are tested and at each step time, the data is collected by the leader vehicle and stored in the data file. The second section is the data processing. This section is very crucial in every project, where we replace the unneeded parts of the data by the useful one, because analyzing smaller data set is easier and faster, especially for machine learning algorithm. The third section is applying the machine learning algorithm to take our decision related to vertical handover. The selected machine learning algorithm fall into category of supervised machine learning, where we have used KNN, K nearest neighbor, support vector machine SVM, and decision trees and random forest. Starting by the K nearest neighbors, KNN, which is a non-parametric supervised learning algorithm that solves the classification problems when we do not have any assumption about the data distribution. In our scenario, which is the sun case scenario, the KNN fails to provide a good accuracy. The accuracy varies between 83% and 89%. The second popular technique used in machine learning is the SVM, that is supervised learning machine. It has been noted that the SVM has two kernels, the linear one and the radial basis function RBF. Results indicate that the accuracy of SVM is less than KNN accuracy, which is approximately 0.65%. The decision tree is not expressive theoretically because it takes only the interference time as a split feature to give decision and ignore the sun irradiance, the relative velocity, and the percentage of packet loss. The first step in our scenario, we should indicate the important features, which are the Platon distance and the relative velocity. Starting by the tree one, if the packet size is less than 38,811 bytes, and the relative velocity is less than 32 kilometers per hour, we should check the throughput. If the throughput is less than 243 megabit per second, the Platon cannot transmit the packet via visible light communication, and we should switch to RF technology. If the packet size is large and the perturbation time is less than 3.5 seconds, which is related to both perturbation resources, switching to RF technology, which is more preferable to prevent information loss. In the second tree, the tree begins splitting by solar irradiation. When the irradiation time exceeds 16.6, the sun almost breaks down the visible light communication. For this reason, the RF technology is more suitable in this case. When the sun irradiance is less than 16.6 dBm and the interference time is less than 2.08 seconds, the packet arrival rate is more than 347 packets per minute. In this case, we should switch to RF technology. In the last tree, when the Platon is highly interrupted and the throughput is more than 3.7 bytes per second, regardless of the packet size, the Platon should switch to RF technology. Now starting by the machine learning classification matrix. The first method in the decision tree is the confusion matrix that consists of 4 outcomes. We have the true positive, when both actual decision and predicted model are switching to RF technology. The true negative, when both actual decision and predicted model are staying with visible light communication. False negative, and finally, the true negative. The second method is the recall precision and F1 measure. Recall present the portion of actual positive correctly classified. The precision prevent the proportion of truly predicted positive. It is used in order to be sure about the prediction. F1 measure is a matrix that combines recall and precision by taking their harmonic means. It's used when we want to have both good recall and precision. The third method is the log loss that measures the performance of models, where the prediction input is a probability values between 0 and 1. The log loss increases as the predicted probability diverges from actual label. The log loss is used for probabilistic classification. AUC ROC area under the ROC curve. AUC ROC indicates the extent to which the probabilities of positive classes are separated from those negative classes. It's noteworthy that the AUC ROC is used for probability classification. Similar to F1 score and MCC is a single value metric that summarizes the confusion matrix. The MCC allows the identification of the classifiers, especially of the negative class samples. No doubt that decision tree is the best algorithm in terms of all the metrics. However, as we have mentioned previously, the tree has just one split. Therefore, we are not able to trust the decision tree of new samples. For this reason, we choose the random forest to make decision during the day. Finally, to conclude our presentation, the crucial step in vertical handover is the handover decision, where we use the machine learning technique, the KNN, the SVM, the decision tree, and the random forest that has the highest accuracy comparing to the other techniques. As a future perspective, we will work to allowing each vehicle to make its own decision. At each interval of time, each vehicle in the Platon will select its appropriate technology according to specific criteria based on real-time learning. And finally, thank you.